Okay, Bismillahirrahmanirrahim. Uh, let's connect what we have learned so far with what is going to follow. So, right now our focus is getting the intuition of things, right? So again, the example that we had seen last time, we have an image, and again the same cheap Mercedes Benz. So this is an, it's in black, right? So it's an analog image, and the Fourier transform of this image, let me draw it here. So we can represent it by big omega 1 and big omega 2, or small little omega 1 or little omega 2, depending upon whether it is normalized or not. So W1 or W2, they are normalized. So they have, so this was the equation if you remember correctly. So this is radians, this is radians per millimeter, and this is millimeter. So it's over space. So this is spatial distance. Is it visible? It's visible, right? It's, let me do this. Okay, it's visible. So the Fourier transform of the analog image, I'll draw it in black as well. So it is this. So it is not the Fourier transform, it is the region of the support of the spectrum, right? So this is something that we have understood earlier. So now if I sample this image, so this is the sampling done. So now in blue I have the discretized image. And the Fourier transform of the discretized image is what? It is periodic. It is formed by the periodic extension of the Fourier transform of the analog image. So it is just the periodic extension of this. So there is one here, and then another one here, another one here, a one here, 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 something is here as well, here, and here. So this is again, this is the one in blue is actually the Fourier transform of the discretized version of the image, and this is periodic, and it is formed by the periodic extension of this guy. So now going back and forth in both continuous and discrete worlds, we need sampling periods or sampling frequencies, right? So we need to know where this is located, and for that we need to know this. What is the sampling frequency? This is T2, this is T1, and sorry. So if what we are given is a discrete image, so in the modern cameras, the image that we get is not the analog image. It is a discrete image already, right? And discrete image is what? It is nothing but an array, and in fact a 2D array of numbers. So we do not know what is the spatial distance between those numbers or between the pixels. So these are all numbers, but they are actually captured from space. So there is some physical distance in space, but right now we only have the discrete image and we have pixels. So we really don't know what was the physical distance between the pixels or between the world points in space. So actually this is missing. So we don't know this. But what we have is a discrete image. So the thing is, it's nothing difficult. The thing is, we can only express the spatial frequencies, this frequencies that are occurring in space, in terms of normalized continuous frequency, little omega. So we work with little omega, we work with these, but not with these, because for them we need to know, let's say 2 pi by t1, and we don't know this. So even if you don't get this concept, it's fine, but this is something that you should know. So now the important point comes now. Now it is interesting to see that what happens in the spatial domain, what happens here in the spatial domain if we sample the Fourier transform of the discrete image. Let me repeat. So this blue thing is the discrete image, and this whole thing is the Fourier transform of the discrete image. And if we just, for instance, imagine this as an image, what happens if we sample it? So again, what happens in the spatial domain, what happens here if we sample the Fourier transform of the discrete image? This is the Fourier transform of the discrete image. Now if we sample it, then what we are essentially doing is we are sampling it. I hope it is visible. So we have all these samples. Again, let me just emphasize. So W1 and W2, these are continuous, right? Continuous in the same way as this analog signal was. And we have our Fourier transform as a continuous value. So the blue part that we already had, all of it, periodic extension of this black part, all of it was one periodic, two, it was continuous, it was analog. And what we did, we just sampled it. So the green part is just these similar sort of boxes, and they are the sampled version of the Fourier transform. And interestingly, what we have learned till now is that if we have samples here and we took the Fourier transform, then we got periodic extension of what was there earlier in the analog part. I'll repeat. So again, what we had learned so far is that the sampling in the spatial domain and then taking the Fourier transform of those samples means periodic extension of the spectrum in the frequency domain. Similarly, if we do sampling, which is the green part, in the frequency domain, then what does it mean? It actually means periodic extension of the discrete image in the spatial domain. So the discrete image, which was in the blue part, it gets periodically extended. I'll draw it with another color. So we have same sort of a discrete image here, so mathematically speaking, here as well. So the way we had copies of this everywhere, the same way we have copies of this discrete signal everywhere, here as well, here, 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 and everywhere. Again, what happened was earlier, sampling in the spatial domain gave us this blue part. What was the Fourier transform of this sampling? Periodic extension of the spectrum, which is this black part. This was the spectrum of the frequency in the frequency domain. So this black part was the spectrum of the analog signal, and the Fourier transform of the discrete signal is just a periodic extension of it. Now an exact vice versa is, if this whole thing is an analog signal, then the sampling in the frequency domain, the green part, if we take Fourier transform of it, it is going to give us what? It is going to give us the periodic extension of the discrete image in the spatial domain. So this is the periodic extension. I'm not drawing the rest. So what do we get? What we are getting is that the periodic discrete spectrum on this side, the green part, is giving us periodic discrete 2D signal in the spatial domain. Now the density of the samples, it varies, and density of the sampling in the frequency domain, the distance between the green parts, is going to determine the period in the periodic extension in the spatial domain. So how far is this going to be from this? It's going to be far, or it's going to be near, or it may alias depending upon the sampling frequency, the green part here. So what happens? The sampling here, the Fourier transform of the sampled version here gives us periodic extension here. If we take this as the analog part, the black and the blue part, and we sample it, then we get a sampled version of the frequency domain. We take its Fourier transform, we get the periodic extension of this discrete image everywhere. Interestingly enough, discrete periodic signal has a discrete periodic representation in the frequency domain. So this discrete periodic signal actually has a discrete periodic representation in the frequency domain. And if we take one period in the frequency domain, let's say this. So I'm now talking about the green part. So they are somewhat similar in shape. So the samples are going to look like this. So all these intersections, they are samples, right? So one period in the frequency domain is going to correspond to one period in the spatial domain. And this is basically dependent on the how the sampling is done. Let's say sampling is done critically. If it is, then actually this is discrete Fourier transform mapping. And what it says is that if we have, let's say, an n1 cross n2 image, which is already discrete, then we can represent it uniquely by n1 cross n2 samples in the frequency domain of the spectrum of the image. So they are directly corresponding to each other. This is the basis of 2D DFT. You've already learned DFT in the earlier course DSP. I just wanted to give you a flavor of it in 2D. So we'll go into the maths in the next lecture. I hope you understand.